transformations, which are going to be really exciting and something we've actually already seen. So spherical coordinates, we've got these really nice transformations over, that is really nice equations that take us from spherical coordinates over to rectangular coordinates. And what we want to do today is look at another example. We're going to be looking at the volume of the solid bound above by x squared plus y squared plus z squared equals z. I'll make sure this looks like z so you don't mistake them for 2's. And below by z equals square root x squared plus y squared. Now, one of the things I got a lot of questions about yesterday was, do I have to draw it? Do I have to visualize it? And the answer is not really. A lot of the times we can figure out the bounds by actually looking at the equations themselves. For instance, here, I know what's on top, I know what's on the bottom. And I don't have to be worried about finding bounds for x and for y, because what am I going to do with this? Am I going to use rectangular coordinates to evaluate this? Why am I not? Why do I know I want to use spherical coordinates here? Because I've got a whole bunch of stuff squared, right? And even better, this chunk right here, what is this? Sphere. And you guys, I love that you're saying that there's a row squared there, right? Now that's not a sphere centered at the origin. How do I know it's not centered at the origin? Because it's equal to z, right? So really quickly here, I'm going to take this over and I'm going to ask, where is it centered? If it's not centered at the origin, we can ask where it is centered. This is the same type of problem we did before when we were looking at polar. So when I ask where it's centered, I'm going to go ahead and I'm going to move that z over. And what am I going to have to do? Complete the square, right? Complete the square. I take the number in front here, and I divide it by 2, so that was a negative 1, so I take negative 1/2. Then I square it, right? And I add it back in. All good? Okay, am I just allowed to add 1/4 to a side? No, if I do it to one side, I gotta do it to the other, right? So add 1/4 over here. Which means I'm going to get x squared plus y squared plus, and this chunk right there is going to factor. I need two numbers that add to negative 1 and multiply to be 1/4. Negative 1/2 and negative 1/2, right? In fact, you're going to notice whenever you complete the square, whatever you get when you divide by that 2 is going to have equals 1/4. That's good? Question? No? Okay, let's think about this here. Where is the sphere centered? 0, 0. 1/2, right? Because the transformation goes the opposite direction, I would think. So I thought it's centered at 0, 0, 1/2, which screws me up, just like it screwed me up in polar coordinates, because my shape is not centered at the origin. Which means just like I had trouble finding r before, now what this means, rho will not be constant. And the reason behind this is the same reason as before when we did r. This means that when I measure rho, the circle is not centered at the origin, so reaching out rho this direction, reaching out rho that direction isn't the same. If my circle is off center, my sphere is off center, rho will take me to a side and all the way across, right? For this reason, when I write out rho, it's not going to be a constant, rather it's going to be a function. What could rho possibly be a function of? Could it be a function of x or y or something? I'm not really dealing with x's and y's, right? What could it be a function of? It could be a function of theta or phi, right? So question becomes, well, exactly what am I going to be doing here? Well, first of all, let's talk about our bounds. We need to find bounds for rho, right? For theta and for phi. In order to do this, we're going to take our two equations and we're going to translate them over to spherical coordinates. So looking at that first equation, let's go ahead and translate these. First equation, you guys told me that was rho squared, right? And what is z? Rho cosine c, right? That's good? Okay, so I've got one equation here. I need another equation, right? Well, let's talk about that one right here. C equals x squared plus y squared. There are two ways to do this. One way is to actually plug in the values. That is, I can come over here and I can look at z. Z is rho, right, cosine phi, right, square root, and I can write the other two down. It'd be rho squared cosine squared sine phi squared. So that was good. I'm going to compare it. I'm just plugging in the x plus rho squared sine theta squared sine phi squared. I want to make sure everyone's following. I don't want to lose anyone yet. Okay? Now, you probably bet this is going to simplify somehow.
Take that out.
We have common terms, right? So what I'm going to do is I'm going to go ahead and I'm going to factor out my common terms. I've got a rho squared and what else? Sine squared phi, right? Which leaves me with the most awesome thing you learned during pre-calculus / trig. What is that, John? 1, which is awesome. We have square root, rho squared, sine squared phi, which is going to give me what in the grand scheme of things? Rho cosine phi equals I've got to be a little bit careful here. Why? Rho could be 0. Rho could be 0. Divide by rho could go to 0. Can't divide by rho because rho could be 0. What happens if I square something and then square root it? What do I always get out? It's going to be positive, right? Is sine by itself always positive? No, right? So what I'm seeing out over here is always going to be positive, but what I have here doesn't have that restriction on it, right? That could screw me up a little bit, so I'm going to have to pay attention to that. Once again, what we just said is when we square something and then square root it, what we get out is always positive. This doesn't always have to be positive. So we could end up with extraneous solutions that don't actually make sense in the context of our problem. Okay, so we raised a really good point here, and that is rho could be 0, right? Well, what does that give us? Well, we're looking for bounds, right? There's one of them. How can I find another bound for rho?
You could divide it off because it's not 0.
I could divide it off, right? Because it could also not be 0. So if I divide it off there, I get rho equals cosine phi. Notice I can do this. I can use my equations to find my bounds because the solid is bound by these equations. So if I want to find my bounds, those bounds are going to be on the surface given by the two equations bounding my solid. Okay, so I've got my bounds for rho. Is everyone okay with that? I need to find some other bounds. What else I need to find? Theta, right? Let's think about this here. I'm going to put this over here. Actually, I should put this in there. We're not quite sure which way it's going. I need to find my bounds for theta, right? I want you to think about the article. I want us to think about this really quick too. Just a second, I want you to think about it. Anyone say anything, I want you to think about it. You know what would be really helpful? That Conex sheet you have for me? That you all kept forever, right? Get out, come on. If it's at home, find a neighbor who likes you a lot. This is a really cool shape. You guys, it might help you to visualize this shape in cylindrical coordinates. What is x squared plus y squared in cylindrical coordinates? R squared. Which would have z equals square root r squared, which is z equals r, which means my height is proportional to my radius, which is a cone. This shenanigans right here is a freaking cone. Okay. Now I want you to think about what this looks like. I am bounded below by a cone. I'm bounded above by a sphere. It's an ice cream cone, right? That's probably not the best way mathematically to describe it, but essentially what I have is a cone sitting below, right? Where is that cone centered? Where is the base of my cone at? 0, 0, 0, right? Is the sphere sitting directly on top of the cone? It's over. Why do I know it's over? Why do I know it's not directly on top? Because the center is not at 0, 0, 0, right? Where is it moved? Is it moved left? Is it moved right? Am I doing the right direction? Where does it move? Up. Up, right? Which means I've still got some symmetry going on, but if I looked at my overall sphere, it wouldn't be centered down here, right? It'd be centered a little above it. So I've got a little bit more of a peak than I would have if I was originally centered at 0, 0, 0. Okay. Now I wanted to draw it to show you that sometimes it's actually easier to talk about the bounds and the functions before it is talk about exactly what the shape is. So a lot of you had questions is, again, do I have to draw it? The answer is no, we didn't have to actually draw this, right, to be able to find our bounds for our interval. Now we're not quite done though, right? We've run into some problems here. I need theta and let's think about this here. If I want to go the entire sphere, what is theta going to be? 0 to 2 pi. Is everyone okay with that? Why? Well, the entire thing, I want to go 0 to 2 pi. I can definitely put bounds in that one. So all I really need is phi. Well, I have two equations for rho up there, and I have this junk that I was busy solving, right? This gave me this. Can I use that to solve for phi? Totally use it to solve for phi, right? Let's talk about how. I'm going to divide rho off on each side. Because I've already accounted for the fact that rho might be 0, right? Let's talk about what if rho is not 0. Two ways to think about this. One, where are sine and cosine equal? Two, I can divide off. Do I want to divide the cosine or the sine off? Divide the cosine. That gives me 1 equals tangent phi, right? So I can either think where are cosine and sine equal or where is tangent equal to 1. That pi over